All right, it should be recording. So I'm talking to Toady again, UK, and he's in the UK, and it's the third conversation, and we're probably going to talk about some more kinetic energy. How I think some very simple arguments can be made to kind of prove it theoretically. And the real game is trying to find some of these experiments that probably should have been done in the last 300 years. I mean, physics claims it takes, 4 times as much energy to go twice as fast in your car. It takes 4 times as much gas to go twice as fast, and yet we can't find a single experiment demonstrating that to be true. But that's what the theory says, and I can make lots of, I think, mechanical arguments saying the theory can't be right because of these thousands of years old instruments. Springs, levers, gears are all free energy devices if the theory is correct, and obviously they're not free energy devices, so what's our choice? It's got to be that the theory's not correct. And so we're trying to find somebody who's adept at preserving the integrity of physics, and will volunteer to have a conversation, explain how I'm a lunatic and how Toady is a dupe for being suckered by my conversation and thinking I have any credibility at all, and that kind of thing. But we can't even do that, frankly. It's hard to find somebody willing to show up and show us how we're got it all wrong. So anyway, Toady, your turn.
Yeah, but by the way, you're not sharing, Gary, so I can't see anything. If you are, or are you just projecting my face?
I
I'm not
am,
sure.
I am, but it should be there. But let me just click a button and see if you can see me.
Hang on, mine.
My
No, I can't see. Can you see me? That's the
Yes,
good.
I got you. Oops, now you're gone. What happened? Oh no, we didn't want that to happen.
No, I can't see you at all.
We have error code now.
Yeah, that isn't good.
Did you change cameras?
No, I don't think so. Should I turn it on and off?
Well, yeah. Well, I don't know what
I didn't
happened.
change anything. I clicked you, hoping that I might see you.
Oh, okay. Yeah,
Hang
something.
on, I'll turn the camera on and off. Right, so the camera's off, and
Okay,
now
now it's on. Okay, good. We got you back.
you got me back.
Yes, you're back. So
All
everything's
right,
okay. So
so
let's
your
just
audience is seeing you
yeah.
and me, and I'm not seeing you.
Okay.
Okay, fine.
Well, I look like hell, and my hair isn't
Yeah,
combed.
all right.
Okay.
It's just in case you draw something on the board. I was hoping to get you to draw something on the board since we can't share on the
Yeah,
screen, right?
exactly. That would be excellent. So again, I'll hit my button once again to see. No, okay, that didn't work. All right, so I can't get away with that. All right, so it pops you back.
All right, how about this? Is it possible? I know you want
Yeah,
to restart.
I'll pause.
Restart. Do a
Yes.
quick intro. All right, so I'm going to summarize where we're at from my notes. Me and Gary have had 2 discussions on this, and we were really looking for someone else from the sort of truth physics type community to discuss this. One person was apparently too busy and didn't want to touch it, I think, for reasons. And then the other did give me a reply, and we will talk a little bit about his reply. But it certainly anyway. We'll discuss the reply that I got. Okay, but general point. It is interesting that if this is something that is really very simple to, is almost so stupid, right, as to be, just a very simple misunderstanding. It's unfortunate that it can't be simply explained what that misunderstanding is. All right. Which is why, again, I'm going to try and simplify what I think some of the challenges are here. Okay, and I know we're going to probably end up having to experiment on this or something. Recapping, we've got some experiments. There was one that a lady did, and there is one that Professor Lewin did. Gary thinks that those experiments on the air track have been, poorly put together or tampered with, and Gary will talk for himself about what he thinks that is. I actually think the evidence is fine, right? Having done the calculations, and I'll explain why I think that in a sec. But whether you think that the experiment is fine and the results are valid, or whether you think that the results are being sort of fudged in some way, you still have this fundamental problem. Right, and the fundamental problem is that when you use momentum and then when you use kinetic energy, right, the two don't match up. Okay, both can't be right given the results of those experiments. Now, the issue, I think, is that when you look at, and we'll go from the Lewin experiment, right? And I think it's pretty similar because we don't have full knowledge of the lady who was sort of just doing a demo, right? We don't actually know how heavy those carts were and so forth. So Gary's got views, I've got views. We'll leave that one. But with Lewin, we're theoretically told what those weights are. The person who responded to me said that what we're missing, we knew this already, but he said, predictably, that velocity has got a vector, and we need to take the vector into account. And if you look at the original PDF I did, the numbers, surprise, surprise, when you look at momentum, perfectly work out if you assume, and we'll draw this in a bit, right, because I think it'll help people, the momentum in this direction, if you deduct that from the momentum in this direction, everything balances and it works, right? The kinetic energy works from the values that we've been given, and the momentum works. If you assume that momentum in this direction is in some way different to momentum in this direction, and if you take this smaller one away from this larger one, you end up with what you essentially started with minus small losses. I have a big problem with that, right? And if that is the answer, I have a big problem with it. And I'll explain why I have a problem with it. Because if you assume that that is a negative and that a positive, there's a couple of questions that obviously come from that. And I'm sure we'll draw these in a sec to elucidate this, Gary. What about something going in this direction or that direction? I guess people would say, you do a vector equation, but anyway. What happens, right, if we very, very simply take the left-hand cart, the slower moving cart, right, the one that would be the negative momentum. I don't like that term, but let's call it negative momentum. The one that we're supposed to take away from the more positive momentum. And if we just hit that into another spring and then send it back in the positive direction, right, you're doubling up even more. Or that cart, we just stop it. Or that cart, we just let it, fall to the ground off the end of the air track, right? We're still left with a overtly, in my opinion, positive amount of momentum in this direction, which is more than the momentum that we started with. And then if I had an air track, I would do this experiment and I would bang 3 or 4 carts of progressing sizes, and we can draw this in a sec to make all this clear with some numbers, into each other, because I would literally have, according to those calculations, and I don't want to use this term free energy because it's like, it's a lightning rod or whatever. But we would have an ability to create more energy, right? Which I find just very troubling, right? Because I don't believe that's the case. So I'd love to do that experiment, Gary, to see, and you'll talk and respond to me in a sec, those carts, right, progressively getting more. So I know it has a vector, and I knew that from the beginning, and I knew the numbers worked out right, but I just cannot get around the fact that you can very simply flip this supposed negative energy, right? So if we tied those 2 carts, so there's 2 carts going in 2 directions, right? So just a reminder, everyone, you have a cart that comes in, and let's say this has got, if we give it the value 1, I think it's about right. Is it, Gary? Yeah, about 1?
Yeah.
This cart goes away, so it hits a cart, and then this cart goes away. This cart is heavier, and it moves at, I don't know, about what is it? About 2/3 of the speed or something.
Well, that's the prediction when they're exactly 2 to 1. So when the ratio is 2 to 1,
so
that would be the prediction.
1, we'll say this is 2.
2/3.
So this goes away about 2/3. Yeah. In terms of momentum, this has what is it? 1.6? Is it?
Well, if you use the 1,
1.3.
it would be 1.3. 1.33.
1.3. Right. So this is 1.3. This is 1. This is 1.3. And then this one, when it bounces off here and it goes backwards, what value is it? We'll draw it on the board, actually.
It would be 0.3.
0.3 goes backwards,
yeah.
Right? So this one, whatever way you're looking at it, has 1.3. And then, of course, this one, the 0.3, now it's bounced backwards, right? If you deduct that from this, you get back to your 1, pretty much, right?
Well, the vector argument, I think, can be just defeated by the simple premise that I think it's a well-established scientific fact that you can turn something's direction for free. I can throw a tennis ball at a wall. It doesn't take any energy to change the vector. So if we know that's for free, I mean, you can do it the hard way, but I'm just saying there's lots of easy ways to flip something's direction, and you won't have to add any energy to do it. You can do it by just going into a gravitational well. One side of the moon, you go in on one side, and the moon will give you the turnaround. You know what I'm saying? You don't have to add any energy to
Yeah, or you
change
have
your
an air
direction.
track that bends round, or you bounce it off.
Well, I just mean that when they landed on the moon, they never had to leave the moon they didn't have to use any energy to get back home. They used the same energy they used to get to the moon, and all they did was do a U-turn to get home, essentially. You know, they spun around in circles a few times and then just U-turned. So I'm just saying it was for free. No energy required. No rockets. They didn't have to use rockets.
Any rockets to return
to the moon. To get back. They were using the same energy they used to get to the moon as the same energy that brought them home. So I'm just saying we know it's for free. So yes. So obviously this vector scalar argument becomes what? Why is this important? Because
it
doesn't.
I don't understand.
It doesn't.
I mean, he says. So the guy that replied to me, right, to present, his view, right, he says, well, it's scalar and it makes complete sense to him because energy cannot be created or destroyed, right? And if you deduct this energy because it's in a vector, it's going this direction, and we'll draw it on the board, right, because that'll make it clear, the 0.3, and you take that away from the 1.3, right, you get left with 1, which is what you started with, yeah? So you've got 1 and 1. And I think that's what Lewin shows as well, which I don't disagree that does work. What I disagree with is that I could take that 0.3 and I could flip it round, right, with hardly losing any of that energy, yeah, just the heat in a rubber band. So maybe you want to pick it up from here, Gary, because I think we both agree on this point. Whether we agree on the experiment and the data that's shown by the experiment, right, we still agree on this issue, I think.
Can you see that?
Yep, I can, yeah.
Okay, well, the audience is seeing a different view, but it has a little glare on it. But anyway, so yeah, it's the one mass hits the two mass. It's 133 going forward. It's 33, you could say, going backwards as a whole number. So you've got 166 as a final result, and you only put 100 in. Now, the trick is that this would sort of make sense, this plus minus thing, if this was a closed system. If you did the experiment with two walls, and you had 133 going this way, and 33 going this way, you could argue that, well, these two impacts would cancel each other. So if you were inside a spaceship and you did the experiment inside a spaceship, one wall would get hit with 133, the other wall would get hit with 33, so those two would cancel and it wouldn't turn you any, and you'd still only have left the 100 extra, right? I mean, the two 33s would cancel and you'd end up with the 100 left over. So 100 goes in and 100 comes out, but it only works in a closed system. Lewin's experiment's not a closed system. Maybe the whole MIT laboratory, you could argue.
Well, this is where we get to, is the Earth rotating maybe a closed system or...
I'm just saying there's no... A closed system has to be one... It has to really look closed. Okay, so...
Well, I don't anything that doesn't... I've had this debate with, other people, right, about whether the Earth is a closed system, and it isn't because, meteorites, and we get into... Let's not go down that route.
Well, I'm just saying that, okay, you could make the excuse that a scalar makes sense in a closed system, but it can't make sense outside of one. So once I allow the experiment to go outside the spaceship, you can't use this idea that this energy can cancel this energy. It's like saying heat could cancel heat, or watts could cancel watts.
Okay, so could we draw our air track? So this is the experiment. If someone's got an air track that I would like to do. So if you could just draw a straight line showing the air track.
Okay.
Do a new one, Gary, yeah. That's it. So straight line air track, right. So if you could draw at one end, they put these elastic bands or springs. They actually use elastic bands in the end to bounce the air thing back. Not that end, the other end. Sorry. So elastic band on, that end. To me, that's your left. Or is this flipped round?
I don't know. But this is just yes. This is the me side. This is the not me side over there.
Right, I'm really confused. But which is your left?
Like I'm looking at the board. How could I tell? Okay. This is my left. I'm writing with my right hand.
All right, great. So you've drawn the spring on the right side, the correct side. Good. Okay. So now if you could draw, just to start with, weight number 1, right? We'll call it number 1, and draw it like just no, nearer the spring because we're going to push it.
Okay,
that's
okay.
it. Not quite at the spring. Okay. Well, that's fine. That's fine. Yeah. Weight number 1. And then just a little bit away from that, weight number 2. Yeah, to the right. Weight number 2. Brilliant. Okay. Fantastic. Okay. Right. And then what are we going to get? We're going to get 1.3, aren't we? Yeah. So how much bigger should we make the next weight?
Oh, you want to show the perpetual
Yeah, I
motion
will show the
machine?
progression.
Oh,
the
yeah,
exact
yeah,
experiment I would like to do.
Okay, so yeah, just go 4. You have to just double. Okay,
Double.
so
All right, we'll do 4.
double.
We won't do any more. We'll just do those. Just do those,
Okay,
right?
and
Yeah.
yeah, so
And
you're just going to bang the 1 into the 2 into the 4, and my argument for how you can really make this work is you just put a lever here at the end. Because a lever will double it too. So
no. So in my experiment, I was
Okay.
going to bounce the 1 off the 2.
Right.
The 1 would bounce back, but it would hit the spring on the end, and it would start coming back. Yeah. Again, now it would start coming in the positive direction.
Right.
But of course, I've got this blinking 2 coming back now, haven't I?
Yeah, well, see, that I don't think that saves you anything. It's easier to ignore the stuff going this way.
Yeah, right, so I'll just drop them.
And
I'll
just
drop them
count
off
the
end.
stuff here, okay? So I actually have the numbers for this. So it's
I'll
you've
just drop
gained,
them off the end, right? That's fine.
so on the
My point is,
first
yeah,
interaction you gain 133. The second interaction you're up to 177. By the third interaction you're up to 234. So you start with 100, all right? And all you need is 4 interactions and you've tripled your energy. So that's how it would work out. So what
am I up to on interaction number 1?
Yeah, so we could just go with 1 ounce, and then we could go 2 ounces, and then 4 ounces, and then 8 ounces.
Okay, and at 8 ounces, what am I getting? Double the energy?
By 16 ounces, you've got triple. Yes, you've got double. It's got 230.
I've got double by 8.
Right.
Yeah, because I'm thinking the air track isn't that long.
Right. 234. Okay. Right.
234.
By the
right.
fourth.
So I've at least double my energy. Now that should be noticeable. I'm thinking that should be noticeable, right?
Well, momentum is weight. I mean, you can't really get around the fact that momentum is a pressure. It's weight. So, like a scale will show you it. You drop. The spring compresses twice for every doubling of the weight. It pulls the spring more. It's a real weight. You're doubling the weights. So by this time, you've doubled its weight. So even though it says, one number, its speed means it's now, it's momentum. That's
all right. So bear with me, because I've been trying to think up a perfect experiment for this, right, where I don't have to have an air track. What happens if I balanced all of these, similar to a Newton's cradle, I think it's called, but didn't quite have them obviously next to each other? I still need the springs. How about if I made weights, with the springs sort of attached to them, like they are on the air track, and I put them in a pendulum type setup? Does it matter how far they travel? Are you with me, Gary? Do you follow?
Yeah, I did the exact experiment. Okay, so I actually have a video with it. Yeah, I used pieces of steel. So I used steel rod, and I had one that was twice as long as the other one. Okay, so one was like 8 inches, and we'll say the other one was 4 inches. And I hung them from a very long string, so they were 8 feet high. Okay, the strings.
All right, so the
arc was very low. Right. And,
okay.
And so I was trying to eliminate as much as I could gravity. Okay, so I would give them a launching speed, and yes, I never got 2/3. I always got half. So all the one object could give was half velocity to the twice as big object. So when the 1 hit the 2, it could only give half the velocity because that was momentum conservation. And the other one didn't go back with much speed at all. It actually, almost stopped or was going, 1/12 of the speed. So you'd have a slight difference, but nothing more than half. Okay, so
your interaction was metal to metal, presumably. You didn't put
I put a spring on it.
You put a spring on it?
Yeah, I put a metal spring. Yeah, a little metal clip. Okay, so it was a little flexible piece of metal. So whatever hit it, it pushed back with exactly the same. So I had to do it with a spring, just because if you do metal to metal, they turn sideways on me a little too much. But the spring worked quite well.
So if Lewin's experiment was correct, I'm not saying it is, whatever.
I'm
but
confident
if
it isn't. So, but yes.
Why would this experiment be that different?
Well, that's exactly.
We haven't got an air track. I mean, where is the lag coming in from this experiment? Because I'm trying to think of a way of doing this without buying an air track. Right, you can see where my mind is going. Yeah.
Well, I think we just need to buy a lever. They're really cheap, or a gear, because all these devices will prove it. Okay, any conversion device essentially proves it, because every conversion device means that every time you hit a light, a low mass into a high mass, you gain energy, and every time you go big mass into little mass, you lose energy. So every time, it's the 10-ton train, 5-ton train scenario, right?
Mm-hmm.
I mean, if I make a 10-ton train into a 5-ton train, I lose a ton of energy. If I make a 10-ton train create with a spring, a 10-ton train, I lose energy. Yeah, making it bigger, I lose. Making it smaller, I gain energy.
Hang on, you're bashing the 10-ton train at half the speed into the.
Well, they're both being banged into a spring. I'm just using any device, like any device you would use to convert them. So you just have them bang into a spring and then lock the spring, and then put the other train there and shoot it. Or, like I said, you have one hit one side of a lever and the other train is set up at the right position. So I'll make the lever argument. I've been making it a lot lately.
All right, explain the lever one to me, because I do not understand it, and I never have understood it. I've watched it a few times, and I don't understand why are you dropping these things onto the lever?
Well, I mean, lever.
Explain the lever argument so I get it. Right?
Okay. Well, I mean, levers obviously are very handy tools, and what do? They convert 10-ton trains going 5 miles an hour into 5-ton trains going 10 miles an hour. They convert 50 pounds of pressure over a longer distance of application into 500 pounds of pressure for a much shorter distance of application. You get me? So they do momentum conversions, right? So you need to convert one form of mass velocity into another form of mass velocity. You're going to get the same momentum out, but you're going to put something fast in, you want something slow out. And that's basically what a lever does for you. So I just have to wait a second for this to dry.
Does it really? Is there not a time interval problem with the lever?
Well, levers automatically, force the issue, because one part of the lever will move faster and slower than the other part because they're connected to each other, right? So you just can't avoid their consequence. So, the idea is yeah, this is the simplest concept. So we'll put the two mass here. And then you can understand that if I put a one mass twice as far on the lever.
Yep.
Okay.
It will balance.
All right. It'll balance perfectly. Right.
You're not moving these masses. You're not dropping them.
Right. Well, I'm just saying. Right. So we will concede that for all intensive purposes, a one mass out here is 2. It weighs 2. Right. There's no way of getting around it. Right. So and why does it weigh 2? Well, because it's moving twice as much in gravity, and this is only moving 1 much, right? That's the key difference. Think about it. Is how much.
Why is it moving twice as much?
See, it's twice as far out. So the arc it's moving on is twice as big. You see?
Yeah.
See, because it's long. See how long that is? It's like the end of the fishing rod. You move your hand a little tiny bit, and the end of the fishing rod moves 10 feet. You get it?
But
I mean,
is
close.
That one mass actually moving, though? You're saying it's actually moving.
I'm saying, well, in gravity, we're actually going into gravity. It's pushing us into the ground, and it's constantly pushing us back up. That's why you constantly feel your ass getting sore, is because it's constantly happening.
Right.
But I'm just saying, just accept that as you don't have to believe it. Just accept it as a premise. Right. And even if you don't accept it, let's just say we make it wobble. All right, you know that even when it's wobbling, it's even. It'll slow. Okay, one side doesn't win. Right. So we know whatever energy we put in, we're going to get even energy on both sides. What I'm saying is the key difference is one side's oscillating this much, the other side's oscillating. So
it's oscillating twice as much.
Okay. So obviously this velocity has to be twice the velocity. There's no way around it, right?
What velocity does it have at all, though? Surely it doesn't have any velocity, does it?
I'm saying we just gave it velocity. We just wobbled it. So this is the wobble, okay? This side's wobbling this much. This side is wobbling this much. All right, so do you accept that?
Yeah.
Okay, so obviously,
twice the distance.
Any spot on here would be going twice the velocity. Any atom on here is going twice the velocity of any atom on here. So any atom on this part of the lever, this part of the lever is going twice as fast.
Yeah.
Okay, so we've automatically doubled the velocity. There's no way around it, right?
Well, yeah, it's just moving twice the distance, which is twice the velocity.
Right, so it has to be twice the velocity, right? So that makes sense. It's half the mass, and now it's going 2v. So it's, 1/2 m, 2v equals the same thing as, the 2 mass times the half the velocity. Yeah, I mean, I'm just saying that's why they're equal. is because this one's moving twice the speed and has half the mass, and this one has twice the mass and is moving half the speed. So the momentums are perfectly equal. That's why the lever works. It's because it's converting one momentum, one speed and mass, into another speed and mass. It's just converting the mass and the speed for us. It's doing, so essentially I could put the 10-ton train here, and I could put the 5-ton train here, right? And do exactly the same thing, right? There would be no theoretical reason for the 10-ton train not to be able to create exactly that.
All right, so you mean rather than having this tug of war like this, you're effectively...
Right, exactly. You're just pushing it through the lever. And we know that if I put a 10-ton train here, we know if we put the 2 here, we know that's going to work. Whatever velocity is here is going to be here. And we're saying that even when I put the one mass out here, this piece of the lever moves exactly the same as it did when a 2 was there. Right? If I took the atom right out of that piece of the lever and I watched it, that atom would do exactly the same thing when there's a 2 here as if there's a 1 over here. So I could exchange the 1 for the 2 and the lever wouldn't know the difference. It would say the same weight was on there. It couldn't tell the difference between a 2 being on here or a 1 being on here. And that's
in those positions.
And that seals the deal, right? Because the lever can't tell the difference. So how could it give more or less energy to something? It can't give more or less when it moves exactly the same. Whether I put the 2 here or I put a 1 here, this piece of the lever moves exactly the same. This piece of the lever moves exactly the same. This piece of the lever will do exactly the same thing, whether I put a 2 here or I put a 1 here. Exactly the same movement, exactly the same speed, exactly the same acceleration. It'll look exactly the same. And that's what sort of just proves that it is the same, because all you're doing is exchanging the masses and the velocities. So it proves essentially that there's no way you could have twice as much energy over here. Twice as much energy goes up in gravity, right? And then twice as much energy comes down. Only half as much goes up, and then only half as much goes down, and twice as much goes up, and then that couldn't possibly work. So it sort of seals the deal, in my opinion, for levers prove it can't work, because this is guaranteed. This location on the lever is guaranteed to have twice the velocity, and if I put half the mass there, I know it'll balance. It works perfectly, so there's no way this can have twice the energy, because it can't get it from anywhere, and it can't give it. We can neither get it and we can neither give it. So how could it possibly exist as real energy? Because it doesn't convert into this object. It doesn't make it go twice as fast. Well, I'm just saying, see, here's another way of looking at it, is a gear.
No, I'm just, no. I'm thinking about the lever, right?
I'm just saying, it's the same argument, really. Because a gear is the same argument. So just think of me, if I had a gear with a small gear here and a big gear out here, right? So it's twice the distance again, exactly twice. And I had it on a rod and I could turn it. Well, if I put a 2 mass here or I put a 1 mass out here, I could never tell the difference. So if I was blindfolded and somebody could switch 1 masses for 2 masses, put a 1 mass here and put a 2 mass there, turning it, I wouldn't be able to tell the difference. They would feel identical, right? But if I did turn it and I stopped at this location and threw the objects, right, from here and threw this object from here, physics says this has 2x the energy.
Hang on, go slow. So it's like a catapult. So
right. It's going to have twice the velocity.
It's going to get thrown.
Twice the velocity for the big
that's got
throw.
Twice the velocity.
Right.
Yeah.
Okay. And this has half the velocity.
Right, yeah, it's got a lot more kinetic energy. That top one.
Yeah. So how can that possibly be true? Right. It feels exactly the same when you turn it. You'll feel exactly the same pressure you're resisting, and somehow you create twice as much energy out there than you did here. Because I could just have another gear do the turning, right? So it's the same rule. If I turn it from a little gear out here, right, I'm losing energy. And if I turn it with a big gear on this little gear, I'm gaining kinetic energy.
Are we saying if we set up an experiment with 2 gears facing each other and we shot the one out of the top against the 2, like its mirror over here, and they hit each other, right? This one has got twice the kinetic energy.
Right, and if you did that on the small gear here and the big gear here, right, and you hit it with twice the energy on the small gear, do you really think you're going to get 4 times the energy here? No.
Yeah, there's our free energy machine again.
Well, I'm just saying it just doesn't,
Yeah.
it fails these really simple tests. Now, yeah, doing them well and with precision and all of that is the real challenge.
I think that is the challenge, and that's what I'm trying to get back to. Is there not an easy experiment?
I mean, in 300 years, they should have, like I said, the fuel one's pretty simple too, right? I mean, somebody should have a go-kart and they should have a metered bottle of gasoline with little markings on it, and just show us that it takes 4 times the gas to go twice the speed. Well, just show us that one. Then why hasn't it been done? It should already be done, right?
Like surely model aircraft people come across this all the time. Wouldn't they be finding, my God, you must never go above
keep your plane, you're barely going, keep it barely buoyant, right? So you're constantly...
if you start to go fast, you use so much fuel.
There's just no point, right? Just keep your plane slow and steady, So big savings.
Big savings.
And the opposite is true in gravity, right? The faster you can get through the gravity, the better off you are. So let me make the gravity argument, just because I think it really illustrates why this mistake was made in the first place, and that's all this was really about, was a misunderstanding of how gravity works. Not that anybody has an understanding now. They call it bent space and lots of different things, but whether the real question is what does it matter when you're going through gravity? Does how much distance you travel matter, or is it how much time you're in the gravity free falling? Which one is going to decide how you derive
options again?
Time, how much exposure you have, or how far you walk.
Mm-hmm. Or the other option is what?
How much distance you go through. So I can do lots of simple arguments, but I'll just use the sunlight argument just as a premise. Okay, so to get a suntan, you go outside. It doesn't matter how fast you run across your yard. You're going to get the same suntan, right? I mean, you can't avoid the sun by running fast or traveling distance. So it's because it's always just about how much it hits you, right? So the simple argument would be is that if you're flying by a gravitational well, the faster you go, the less you get bent. Now, in theory, you should get bent the same amount if the gravity was some sort of constant thing that just affected you based on the distance you travel. But the fact is, it's just about how long you're in the gravity. So the faster you go means you get through the sun really quick. So I run from my garage to my house, not that they're very far away, but I can only get a certain amount. I'll get less and less sun the quicker I make that trip. You get it?
No, I'm totally lost now. So go back to the gravity well.
I so just think of rain then. Just think if gravity was.
No, I get the sun and the rain. Like the more you're in it, the more it affects you. But why is that with going past the Earth? Surely you want to go faster, so you're in it less.
That's exactly what I was saying. So the faster you go, the less of it's going to affect you. Because why is it going to affect you less? It's because you're in it less time, right? The gravity's only in this little section. The faster you go through the section, the less you can be bent by the gravity. Right?
Yes, I agree with that.
Okay. So I'm just saying it shows a pretty clear correlation between it's just about how much time you're in gravity, not how much distance you're traveling. So it doesn't matter how big I make the distance.
I'm stupid here and not realizing something then.
Oh, come on! It doesn't. All right. So I just get to the next
part.
Cut
to the chase,
so let's just draw the 4 times difference. Okay, and that's the one that really where this whole thing of 4, because originally it was 4 times the energy. It was just mv squared, and that would have been 4 times the energy in the experiments we've been talking about. If we believed in mv squared, it'd be 4 times the kinetic energy. Because they put the half in front of it, it's cutting those numbers in half. Okay, so it's making them more reasonable. So you go 4x the distance, okay, just to get to just double the velocity. So you want to get the velocity to double, you have to go 4 times higher to get the velocity of an object to double when it hits the ground. And the idea is they're counting each piece of this as if it's a piece of, like, you get 9.8 meters per every 5 meters. Let's just make it 5 and 10. Do you understand that part?
No.
We'll say gravity's 10 meters per second.
All right, 10 meters.
Just to break that. Okay, the fact is to go 10 meters per second, you only travel 5 meters. So in the first second, when you're in gravity, you only travel 5 meters. Your speed will be 10 meters per second, but you only went 5 meters to do that.
Right, now you've lost me. I thought the speed of gravity, let's round it up to 10, is 10 meters per second.
Right, but you don't actually travel that full 10 meters because when you fall in gravity, you fall slowly at first. And then you get up to 10 meters. Your maximum speed is 10 meters per second, right?
Okay, so how much do you fall in the first
Yeah, so
period?
the first, yes, it turns out to be 4.8 or 5 meters per second. That's how far you fall
from
to get to 10. Right.
Right, okay, yep.
All right, so in 1 second, you only go the 5 meters.
Mm-hmm.
Right?
I'm with you so far, yeah. Okay,
Right,
so you're
right.
starting off stationary. I'm letting go of an object.
So
It's
these
gone 5 meters in the first second.
So how they're looking at it is they're saying when you go up against gravity or you're falling in gravity, the 4-time object gets it goes 5 meters here, 9.8, 9.8, 9.8, 9.8. When what really happens in the real world is, no, you get 9.8 here in the first second, and then the second is 3 of these nodes. 3 5 meters, right? So you don't get 9.8, 9.8. You only get 9.8 for that whole group. So you do this second travel. You travel this bigger distance, and the third second is 5. This is Galilean stuff. So Galileo figured out that it's all odd numbers. So it goes 1, 3, 5, 7, 9. It just keeps doing the 9. And those just happen to do with the rig. So what they did is they're saying, well, if you go up against gravity, you have to defeat each one of these 9.8s. When no, your velocity you never get to add all those because these seconds, right? This 1 second wipes out 3 of those. You get it? So the first second.
No, I don't.
Right, so the first second.
Go really slowly. Go really slowly because I haven't been thinking about this as long as you, Gary. Go slowly.
Right.
First second.
So
you go 5 meters.
So the sun is shining, and the first second you're sitting here, and this is all the distance you do. Is this lousy 5 meters, right?
Okay. So the first second I drop 5 meters. I've got that.
Okay, and you're half tanned already, right? But you're only going to get a 2-second tan, right? So just wait. So you've gotten that much sun, so to speak. The second one, you're going 9.8 meters, plus you're going to get added more velocity because you're still falling in the gravity. So you're already going 9.8 through to the second. So the second.
Hang on, how can I be going 9.8? I thought I was traveled off only 5 meters in that second.
I know, but after the 9.8, you're traveling. Your actual velocity is 10. You start at 0. You start at 0, and you're going to end up at 10, right? You start at 0, and you're going to end up.
That's my maximum, though, right? That's the
right.
The
That's
maximum
your end velocity is going to be 10. So you're going 1 mile an hour here. You're going 2, 3, 4, 5. You know what I mean? So you can just go right up to the 10. So the whole trip, you started the trip only going 1, so you only get a 1 for that, right? You started the trip going really slowly, so you're not making up much ground.
You lost me. I'm lost.
The 10 meters
per second. I've lost the explanation. So go slowly, right? Because like a lot of people, I'm getting muddled up between the acceleration and the velocity. Yeah?
Right, okay. Right. Well, as you step on the gas pedal.
Just do it by meters, right? Because you drew it there nicely, right? So do it. Just literally put the numbers there, so I get it, right? Because I think you're trying to explain something quite important that I'm not understanding. Okay, and that's frustrating me.
The first millimeter, you don't go very fast, right?
Yeah.
Okay, you're going really, really slow. You're getting very little distance. And so the second millimeter, you're going a little faster. The third millimeter, you're going a little, you know what I'm saying? So you're gaining the velocity as you fall. So you finally get to 9.8, but you started at 0. So most of the trip, you were going much slower than 9.8.
Yes.
Most of the trip, you were only going this, it averages out to this 5. You get it? It averages out to 5.
You said the first second I go 5 meters.
Right, exactly. That's how you get to 9.8, is going a second. You have to fall a full second to get to 9.8. You can't fall a half a second and be going 9.8. You have to fall a full second to go 9.8.
So in 1 second, I'll be going 9.8 meters per second.
But my average for that trip, but your
the
average for the trip,
that distance, of that second is actually 5 meters.
Right. That's your average speed.
Right.
That was your average speed was only 5 meters. So what you only got
that. Yeah,
you only got
because I'm
5.
going 10 here and I'm going 0 here. So it's 5 meters I travel, even though obviously by the end I'm going much faster.
Right.
Okay.
Right. So that's
then what happens?
Those are the units. So I'm just saying. So this one only does the 1 second thing. It gets 9.8, right?
Yeah.
Okay. So I'm gonna drop it that 1 unit.
That's all it gets to. It goes 5 meters, and it's going 10. Yeah,
right.
Well,
so this one is now going to fall 4 times the distance. And why is it 4 times the distance to go twice the velocity?
Why is it 4 times?
Because this part, your average speed is going to be 15 miles. Okay, your average speed here is 3 times your average speed for that first second. So the first second, your average speed was 5 meters per second. Your average speed for the second is 15 meters per second. So you're racing, you're racing through the second. The second, you're 3 times as much distance. 3 times the distance you've traveled in that 1 second.
Now I'm with you. You're really racing because you're already up to speed somewhat.
Right. So the same rule applies when you're fighting against gravity. The faster your velocity.
Right, so to begin with, I'm going relatively slowly, that first second. Second, I'm really wishing for it.
I mean, 3 times. It's 3 times. And then it's going to be 5 times the, and then it's going to be 7 times the velocity. Your average velocity is going to be much greater than it was for that first second. So
okay, all right. I've now got it. I'm a bit slow, but I've now got it. Yeah.
So you just invert that. So if I wanted to launch something, I've got to launch it at twice the velocity, and I'll end up 4 times higher because the initial launching speed is going to be 15 miles an hour. So I'm going to travel the first second without getting in much gravity. Right. I went a huge distance in the first second, and I only slowed down by 9.8. You get it?
And then the second, you're going to get all of this gravity hitting you.
Right. Well, it's going to be a higher percentage of my velocity. So it's going to wipe out more.
As possible in that first second, then. I really want to set off for the tremendous speed for that first second.
Right. So if you want to go to Mars for $1.
Hang on. So that means the gravity is affecting me less in the first second. That can't be right.
Yes, of course. Well, it's affecting you.
Is that true? Is that true, Gary?
It's affecting you per mile much less. Yes, you're getting 50 miles per gallon in the first second, and you're getting 1 mile a gallon in the last second. So your efficiency goes way down as you start losing your velocity. So when you have a high velocity, you're getting through the sun really efficiently. No sun is hitting you. When you're going slower and slower, more sun is hitting you. Right? You're getting burned up. So in the last second, you burn 100 times more than you burned in the first second. You get me? So the slower you're going by the sun, you can get it, the hotter it's going to get, right? So the fast part, you're barely getting burned. It's only that last second that really cooks you, if you could think of it in that metaphor. So it's just about time you're in it. So the 4 is just 2 seconds. So it's twice the velocity. So you take 2 seconds to fall 4 times the height. And the only part that matters is the 2. So all you've done is double the velocity. You've only doubled the energy. It's not 4 times the energy. But
hang on. So you're telling me in 1 second something will travel 5 meters, and the same weight if I drop it from, what are we saying? What's the height going to be?
4 times. 4 times that height.
4 times the height, 2 seconds.
Right.
Not double the height.
Yeah.
4 times the height.
Right. I screwed up on this very subject a few months ago. I made a whole
So is
video.
that true? Is that genuinely?
Yes. It's 4 times. To double the velocity, you go 4 times higher. But remember, it's just about how long you're in the sun. So the only thing that matters is how.
Me is this first second of. Surely all these rockets want to make the most out of that first second because they are almost getting
that's exactly what they do, though. That's exactly what they do. They try to get up to the fastest speed they can as soon as they can, because that's how you save fuel. So the bigger you always want to shoot for a further location.
But why is it 1 second? Why isn't it 1 year? Right? I mean, a second is an arbitrary measurement.
I know, because the sun. Okay, what you're saying, why do you tan at the same rate per second? Well, because that's the rule of the sun. So
Yeah.
gravity, that's the gravitational rule, is that it's a constant.
And what is the gravitational rule? That you tan at an incrementally different rate?
No, that you're tanning at exactly the same rate. Again, this is me telling you that it doesn't matter how fast you're moving. I can dance in the sun, I can prance, I can climb a tree, I can run 50 miles an hour, I could run 10 miles an hour. I'm going to get exactly the same tan. No matter what I'm moving, who cares? Where I move.
You just told me, Gary, you've just told me that first second, in fact, you've proven it to me, right, is more important. Because you flipped it around, right? You were dropping down, yeah? But the point is going up, you're fighting against the same thing that's coming down, right? So you're saying that first second is really important.
I'm saying the seconds are always important, and the distance you travel means nothing to gravity. Gravity can only affect you over time. It can't affect you over a distance. So you're traveling 3 times the distance, but gravity only gave you 1 increment of velocity. It only gave you 1 9.8. You didn't get 3 9.8. You only got 1 9.8 in that whole second. That's why your velocity is only twice as much and not 4 times as much, because you didn't get 4 times. You didn't get 4 times the energy this one got falling just that one distance, because you broke some of the distance into this shorter amount of time. I'm just trying to get to the point that gravity, you're only acquiring it as long as you're in it. And as soon as you're not free falling in it, you're not getting tanned by it. You're not collecting it.
But I'm completely lost about when you flip it around and you got a rocket or a rock or anything that you're firing upwards, right? Why gravity should care that you're spending a second or not, right? Surely gravity is gravity, and it's just there.
Well, that's what I'm saying, is you should care if you thought about it as money falling from the sky, then you'd understand what I'm saying, right? So just think of it as nickels falling from the sky, right? So let's call gravity money. So money's falling from the sky, and you have a bucket and you want to collect it, all right?
Yep.
Does it matter whether you run towards the bullets, the money, or you run away from the bullets? The money's falling at a very fast rate, right? Speed of light. So it's not going to matter whether you run or you go sideways or whatever you do.
Couldn't care less.
You're just going to collect nickels in your bucket. So it's just about how long you're in it. So it doesn't matter that, yes, okay, in the first second I travel 3 times the distance. It's only 1 second worth of collecting. So as I'm going up, I'm only collecting weight. So say if the nickels were weight and they were going to push you back down, right? Mm-hmm. So you get it. The first second, okay, I traveled 3 times the distance that I'm going to travel in the last second. But guess what? I'm going to collect 50 nickels here, and I'm only going to collect 50 nickels here. Same number of nickels.
So 50 nickels, 50 nickels.
It's just the time that matters. So I traveled this huge distance, and I only got 50 nickels for my trouble. Right, and I travel this tiny difference, and I got 50 nickels for that trouble. So you know what, you get it. So it's, if you thought about it as weight, knocking you down, taking away your energy, you can get to 0 here. You just understand that the faster I start off, the more distance I get with very few nickels.
I
collect very few nickels. I collect very few nickels.
Collect less nickels.
Exactly. If I can go thousands of miles an hour through the space, well, then I'll collect very little nickels.
So actually I want to spend, which is true, of course, as little time as possible in the gravity. Less time is better. Yeah, because I'm losing less energy.
The catch is that you can trick it in the sense that you can drop things on a staircase, right? And then it really is per second. You know what I'm saying? Then you're only counting the free fall time is the only time that matters. So it really is you have to understand gravity. You have to be free falling to collect nickels. It's like your bucket can't collect them if you're sitting, on a chair. You know what I mean? They bounce out of your bucket if you're sitting. You can't collect the velocity, if you get what I'm saying.
No,
you can't collect. Only when you can collect.
Go back to a rocket, it's going up, or a stone, or whatever, a bullet going up. Doesn't matter. Rocket going up. Yeah. Okay. That first second, right? If we're going fast, we can go a lot further in that first second, right? And the energy cost of the gravity that's pulling us down. I'm assuming all the time that you've been talking about the gravity that's trying to fight against us.
Right.
Is that what you have been talking about?
Yeah. Well, I'm just saying. Yeah. Well, I'm just saying. If you thought about it as just weights that you were collecting, and you're getting heavier and heavier, the more you collect.
Yeah. Someone's putting these weights on my neck or whatever, right? As I'm going upwards, yeah.
And they're doing it by time. They're putting them on by time, and so the faster you get out of that jail, the less weight you're going to have on your neck.
The less weights I'm going to collect around my neck. Yeah.
So it's you could eradicate all of Earth's gravity in a sense, right? If I could leave, 99% the speed of light from the Earth, you could understand that it would cost me almost nothing to leave Earth, right? Because I'd be going through the Earth's gravity so quickly. It'd be one billionth of a second is all I'd be in it, and
it'd be negligible,
right? So it'd be a tiny cost to get off the Earth. But I'm obviously going insanely fast.
Yeah, insanely fast.
So if I'm going to Grandma's house, I'm going to go way past Grandma's house.
So you really want to get off the Earth very quickly.
Yeah, the quicker you go, the less gravity that'll
Because
affect
also you've got this incremental thing of rockets for the fuel for the next second. You need all that fuel to get that there for the next second and so forth.
Right. But
which is why they keep coming out with these idea of these monofibers with skylifts and things to try to get you to a higher point.
Exactly, where you don't have to...
get out of the gravity well more, and then it's a less cost, isn't it?
Exactly. That's free energy, frankly. I mean, space...
it's free energy, like 20 miles up.
Right.
You can...
It's perpetual motion anyway. Right. It's a perpetual motion once you get into space, but, till then, you've got to pay for it. But this is the argument where I think the whole thing went sideways, is because the visual of that 4-to-1 ratio is so... It's sitting right in your face saying, what do you mean 4 times higher is only twice the energy? That's stupid. I mean, it's such an obvious visual. I mean, the 4-to-1, and somebody's going to tell you that's really 2-to-1. No,
hang on. Explain the 4-to-1. You've gone too far.
Well, I just mean you're dropping an object 1 unit of distance, and then you drop it 4 units of distance, and you only get twice the velocity. That just doesn't make any intuitive sense. I mean, it just says right to you, what do you mean 4 equals 2? No, I know.
Yeah, surely it's going to be twice.
Well, yeah, it has to be. They can't 4. So
4, it doesn't make sense. I'd say, well, just twice, and then I'll get twice.
Well, I'm just saying that it's twice the velocity, but I just mean, somebody just, you look at it, you say, I can do this obvious mass, 4-1. I can see the obvious mass.
Oh, hang on, you got 4 times the mass. I thought it was 4 times the distance.
No, I'm not changing the mass. Sorry, that's distance.
Yeah, don't confuse me.
Okay, on purpose.
So, I'm assuming what you're saying is this. We'll go slowly. I'm assuming that if you took a mass and you dropped it, what's your distance in your first one?
It doesn't matter.
Point to your circle. To the right, what's your distance in the first one? What distance are you talking about?
This is just 1 unit, so it's just one...
All right, we call it unit, right. So 1 unit, and I would assume that you took the same mass, we'll call it a mass of 1, right? You dropped it 1 unit, you've got 1 velocity. I would instinctively, incorrectly assume that you took 1 mass, and you put it 2 units up, and you drop it, and you'd get 2v, right?
Exactly.
That's what I would assume. That would be my intuitive... incorrect view of it. Right, okay.
And that's where you can just see that if I just did the subtle trick of putting a half mass here, that's the trick, right? Because the half mass going 4 times higher, right? Okay, it's
hang on, half mass? Why are you putting half mass there?
Well, I'm just to point out that you can just see the simple trick that's half the gravity that's going to affect it now.
Now you've lost me. Go slowly. What are you doing with this half mass?
I won't lose what I've already got. So just ignore it. Pretend I didn't say anything.
Right, because I need to go and think about these things. Because
I just want to get the point across. I just want to get the point across that back in 1600s, this was a complex argument that had to be solved. Okay, it did look like it seemed a very confusing statement from nature, because they
agreed.
Because they sort of
the heck out of me why that should be.
You're right. They sort of knew that hey, it's only twice the impact. They sort of knew that it worked out that this wasn't 4 times as powerful, but it obviously doesn't look right. 10 feet, I go 20 feet higher, and I don't have. Right. I can't get 20. I can't get twice as much energy. That
looks dreadful.
But it's just because we're not really seeing what's really happening in your nickel collecting. It's all about time. The distance is not relevant. Time. It's twice the time, and that's what you needed. You had to go 4 times higher, or you wouldn't have 2 seconds worth of falling time. If I put it twice as high, say if this is 10 feet and I put it 20 feet, in 20 feet, I'm only going to get 1.3 seconds worth of fall. right?
Yeah, but hang on, if I'm working, hang on, Gary, can I not just say, well, I'll just, instead of all this effort to get this one mass, right, 4 times higher to get the 2V, I'll just stick 2 things, 1 measurement high. I'll take, 2 balls, right? You've got balls there, cannonballs or whatever. So I just take 2 cannonballs and I'll put them 1 unit high, and I'll get 2V.
You won't get 2V, 1 unit high.
Well, 1 gives me 1V.
Oh, right, but you doubled the mass, so it's right. What you're saying?
Yeah, I've doubled the mass. Yeah, even better. I'll double the mass. All right. Yeah, I mean, take 2. Yeah, double the mass. Yeah.
Yeah, well, that's the whole point. Is that that's where it's about velocity. So you can play with mass, and it'll add up. You know what I'm saying? The mass doesn't get you into trouble. It's the velocity that creates the problem. Everything falls at the same rate, so you can't. I can make it an elephant and a piece of dust.
Yeah, an elephant. And
a piece of dust. Now I'll get the same problem. I'll drop the dust 1 tiny, foot, and the rule will be, well, you have to drop the elephant from 4 times higher, to get the same speed. So I can't, even though it seems ludicrous that the dust can't beat the elephant to the ground, the fact is it can't.
Hey, what?
Well, I'm just saying that it's still 2 seconds. If I put, I can't change the rule of time. The dust
Rather than
will.
Dust an elephant. Let's take an elephant and a peanut. Yeah.
Right.
I always thought the rule was if I drop them both from 4 high, they'll both hit the ground.
Right. But we're not going to drop them from 4 high. We're going to drop one from 1 high. We're going to drop the peanut from 1 foot, and then we're going to drop the elephant from 4 feet. And the thing to understand is that the elephant's
now what's going to happen when you
the elephant's going to take twice as long to hit the ground as the peanut.
Yes, correct.
Okay, so that's the part again. Yeah. Big intuitive problem, right? You're saying how could that be true?
The elephant's so much bigger, you'd think that's ridiculous. Why is the elephant not hitting the ground?
Yeah, it's like the elephant would be floating. The peanut would be looking like it's racing to the ground, and the elephant's just taking his time. Because it still has to collect to
Well, it's irrelevant at the mass, right? The
mass is irrelevant to an atom. The atoms. Look, basically, I would argue gravity's a nuclear force. The only thing really moving are electrons and protons. So, they're all the same size. That's why they move the same speed in the gravity. So they're the buckets.
Right. So it doesn't matter how.
They're the little buckets collecting the rain, and so they always have to fall the same speed because they're the same buckets. Standard bucket. Standard bucket, standard rain. So the rain is standard, the buckets are standard, and you really don't have any options. In terms of playing with mass, you have to. The only thing you can play with is how long you're in the gravity, your velocity.
There must be some learning that they made there, though, right? To do with, I'm just thinking, like in wars, right? To do with dropping things from battlements and things. There must be some anti-intuitive discovery. But anyway, I'll have to go and think about that. Yeah. You know what I mean? Whether it was better to,
Well, it's another argument. Like, look, the ballistic gun nuts, they have these conversations because they know kinetic energy doesn't work. Arrow people, they know lighter arrows, forget it, doesn't work. And I'm sure catapulters from 1650 would tell you that, no, I'm better throwing cows than sheep. I'm better going with if I can get the heavier object to actually get to the location, I'm going to get more bang for my buck, and I'm certainly not going to gain more by going lighter. I might keep the same, but I'm not going to gain any energy. So they knew there was no free energy. They knew the levers just convert. And the trebuchet,
I'm thinking the trebuchet is a good example.
Because, the pure one, right? I mean, if you have a pure trebuchet, it's working based on gravity, okay? They use weights.
Oh, you mean the one with the weight on it?
The more modern ones, they use rubber bands and all that stuff.
Yeah, I'm thinking of bands, but
okay, but the original was just to lift the big, heavy weight up and then allow the heavy weight to swing a big, long arm. And the further out you go out on the arm, the higher and higher velocities you can achieve. Now, obviously, you can't put an elephant on the end of the, trebuchet, but the fact is you can go with a much lighter weight, 10 times the distance, 10 times less weight, and you could get a substantial 10 times the velocity. And that was basically all. But you can't really change the fact that, you have to conserve.
Design should be a good example, actually, right?
You have to conserve the momentum, and so you're really just turning this distance, right, into the big distance. All right, so you go with the lighter object.
Sure, but if you've got a big weight here on your right of the fulcrum, and you've got a strong enough arm, not too long, but strong enough, you can throw a big rock over a wall or something.
Exactly, but I'm just saying that what you're really doing, though, is just taking something that has a very big mass and a small velocity and converting it into a small mass and a big velocity.
Bigger velocity, yeah.
All right, so that's all you're doing. You can't make energy, you just convert the relationship between the MVs. So whatever energy you have here going down, okay, is exactly the same energy you got going up over here.
How did they wind that mass up? Because they used like really heavy stones and things in baskets.
Yeah. Well, they would just do it by the same thing. They could either put it on a pulley with and use a pulley to pull it up, right? Or they would just pull down on this. They take a string, and tie it to the top and just pull it down this way, because now they get the advantage of this is only 50 pounds of pressure over this long distance, and that'll make 500 pounds of pressure over a short distance. So it's just
like they did do it. They didn't have a basket and just put individual rocks in it till they were enough, and then pulled a stop out, and it just went down. They did what you said today on
They trebucheted the weight up, and then they allowed the weight to swing and throw. But yeah, I mean that's all a lever can do. It just can do the conversion for you. It takes something that's got 500 pounds of pressure, and it turns it into something with only 50 pounds, but you have to do the longer distance.
Yeah, but with the trebuchet, you don't mind the longer distance.
Yeah, no, I'm just saying it's a huge. I just mean that it's an equality. Okay, there isn't. I can't make and I can't destroy.
You're not making anything.
I can't make more energy by doing it one way, and I can't destroy energy by going the other way. When I'm pulling it down, I'm not losing energy, and when I'm letting it loose, I'm not gaining energy. You can't, because theoretically, the only place the only way kinetic energy theory could work is it would have to take me more energy to pull it down than when I released it. And obviously we know that's,
Well, that's not the case.
I'm just saying it's conservative. So, you have to conserve the energy, and kinetic energy breaks that idea. So the 10-ton train, 5-ton train does the same thing. It just breaks the whole idea of the conservation of energy.
Return to where we started, right? What experiment is possible to put this to bed? Because you said, I think 3 interactions, 3 collisions, would have doubled the energy of the initial, whatever.
Well, I guess all they have to do is prove that a spring isn't conservative. So, I mean, this was a simple experiment that they don't seem to be able to do competently, but you just shoot the 10-ton train, you know what I'm saying, the 5-ounce train. You shoot the 5-ounce train going 10 miles an hour into a spring, and then you shoot a 10-ton train going 5 miles an hour into a spring, and you see if they compress the spring the same amount. It means they weigh the same. It means they have the same momentum. It means there's no kinetic energy, because you won't collect. The 5-ton train should have twice as much energy, right? If it has twice as much energy, you should compress the spring twice as much.
So the 5-ton train going 10 miles an hour rather than the 10-mile train going 5 miles an hour, it should have more kinetic energy, of course.
Right, it has to compress the spring
more.
Train. It has to compress the spring some more because it has twice as much energy, right? So
does it? Is that how you measure kinetic energy, by compressing a spring?
Well, a spring is doing weight, right? And you know that if I have 300 pounds sitting on you, or I have 600 pounds on you, you know that 600 pounds is twice as much energy as 300 pounds sitting on you, right? I'm just saying that. I'm just saying you can understand it's a weight argument.
Yeah, but it doesn't. The time that pressure is being exerted on the spring come into it, right? Because
I know, but that's what makes springs useful, is the fact that they're within a range. They don't care what speed. I could compress the spring.
Do they not?
I can compress the spring really
slowly.
Well, can't you imagine me doing it really, really slowly, and then I have a little clip that stops it right there, right?
Yeah, I can.
And then I can do it really quickly, and it's the same location. It's the same compression. It doesn't care how fast you compress it. It just says, compress me a certain location, and I'll give you back a certain amount of energy. So it's just about how compressed the spring is.
Well, there's no way you can hit a spring so fast.
Of course you can. You break it with a bullet. You could shoot it. See, the problem with a bullet is that it's the transmission speed through the metal. It takes.
That's what I'm saying. The transmission speed. This is what I'm worried about with our train and the.
Yeah, I know,
spring.
but we're only going 10 miles an hour. That can't break.
Oh,
that
we're
wouldn't
pretty
hurt
slow,
it.
aren't we?
Yeah,
Okay,
So,
right.
so that speed won't be a problem for any spring.
All right, then why can't we do that? That's a good experiment then. Yeah,
Yeah,
we'll get two masses. We'll move them at a set speed, right? That's half of one, and we'll get it to.
I know. I've sort of did half the experiment with
Oh, you
ball
did?
bearings. Okay. Well, yeah. I mean, I used ball bearings, and I was pushing them with the same spring. All right. So I would push one ball bearing.
All right, so that's fine. That's
So I used one and
No
pushed it, and then I would use two and pushed it with the same exact compression. So I pulled back a rubber band, so to the
Right.
same location, and then
Yeah.
shot them. Okay. And I got results that are close. You know what I mean? They weren't perfect, but they were close to 50. You know, the when I shot two of them, they went half the velocity. And when I
what
shot one,
surface did they go over? This is the
well, I made a little track. Like I said, it wasn't perfect. It wasn't a perfect experiment. That's why my numbers weren't perfect. But I'm just saying I could perfect it. I could make it
So
even.
I've got. I don't know. Can you see this device? You
Yeah.
must have seen one of these before, right? Yeah. So
Right.
look, I got this little spring here, right? Yeah, and this little. I could do something with this, right? And can you see this?
Yeah. The only bad side is it's got a little slope on it, so you have to change it so it. You
Yeah,
have to.
I know.
You
I
have
had to change this. But
you
I
have
can change
to-
the knob, right? But this goes. Look, it goes. It's always the same, right? It's got a spring. It's got a.
Well, you
You
think
know.
they're always the same, but you know their quick releases are a little more complicated than you think they are.
Oh, are
Because,
they?
Well, yeah,
If
I found
push this
with
quickly.
yeah.
Maybe.
There are a tiny bit. There is some fluctuation. In them.
Oh, there is. Yeah. If I push it, you're right. If I push it quite quickly, it tends to go way
Yeah,
quicker.
so I
doesn't it?
had to. I used a clothespin. I had to put
Oh.
a little pin through it, and then that went around a piece
I
of
thought I
fish.
had an ideal little thing there that I could rig up with a little ball in a little runway.
I'm just saying what I've learned is you have to really. There's little subtleties to all the engineering,
There are,
and that's why it should be done with people with lab coats. It should be done with people that can.
It should be done with people
who can
proper
control
mechanisms.
all of these little variables that can
Yeah, 'cause they
screw
matter.
everything
Yeah.
up, you know, because ideally, like I say, even when I did the ballistic pendulum, you know, if I could solder a couple little eye rings on the piece of metal to make sure it can't oscillate back and forth and run a piece of fishing line. You know what I'm saying? I'm just saying it ends up being a lot of work. You know, you got to fiddle with all these little pieces to get
Yeah, all
everything
these
right.
little things together. And the more complex you make it,
Yeah,
the more variables you're introducing.
You know, and it's in the middle of your living room. You know, so I mean, you know, but I just mean that I wish, you know, I mean, we should be able to get a physicist somewhere that can do these experiments. Or I'm just saying, one of the tinkerers out there, all these guys doing the free energy experiments. You know, one of them, you know, they're making all kinds of, you know, the Tesla guys, you know, they're making all kinds
crazy
of
stuff.
Yeah, why we got to be able.
Why don't they just do this?
Yeah, let's get somebody to do this real experiment, you know, instead of doing all those fake ones. You know. It is frustrating.
It is frustrating. All right. My head's done in now.
Yeah.
My mind is totally blown by the 4-1 because I wasn't aware of that at all, right? Which is on me, really.
And then, well, the lever argument too. So you're a little more convinced about levers
I'm
too,
clear
right?
on the lever argument,
Okay.
right? I'm still worried that I'm being an idiot and someone's out there watching this shouting at me, Toady, you freaking idiot.
Well, I'm sure there's plenty of people doing that.
You idiot!
But they're
you
not.
just don't understand.
They're not doing.
Look, I'll place the audience, your audience, wherever it is. There's the camera, right? Please, just go and make a video, like with no swearing or anything in it. I'm not swearing. I'm not being nasty. I'm not calling anyone idiots. Gary's not calling anyone any idiots today, right? I know he gets
Today.
sometimes, but when I'm there, he's more moderate, I think. So please go and make a civil video. Really simply, number one, please do the experiment, right? Do some of these experiments we're talking about and show me, right? Because I'll believe it, right? Yeah,
Or find links, or find links to somewhere where they have done them. I mean, just that you would think in 300 years, like I said, these experiments would be even notes taken, something, you know, to have nothing.
You know, like, look, if there are tinkerers out there, right, you could do any of those. Like we've mentioned, probably 10 different experiments today, right? I like the energy. It's a really good closed system. I like the one with the plane or the model car running from the fuel, right? Because your only energy you're putting in is the fuel, right?
Right.
You go whatever, twice the speed, 4 times the fuel, you know, that should be provable, right? So please go and make a video, post it up, put the link in, let Gary see the link, let him okay your link or whatever, yeah? and we'll go and look at it. I promise you, right? Because I'm very open-minded on this. I'm willing to be proven absolutely wrong. Yeah, I genuinely am. Yeah, but you know, I'm almost without words because this should be such a simple thing to find some evidence of it somewhere, right? It should be easy to find some evidence.
Yeah, and the only thing, like I said, that gives it away for me is that when you read the history is just as bad as the present, in the sense that all these decisions were made without
our correspondent
without physical evidence. That none of these people had any hard evidence to convince them, but they were still convinced. And then you have that magical moment in 1940 where they put the 1/2 in front of it.
Was it as late as 1940?
1840, sorry. 1840. You know, that magic moment where all of a sudden, let's just change it by 1/2. That's not a big change.
Our correspondent claims that the formula... Did you read what he wrote? Yeah, he said it could be derived from Newton. Did you read that?
Well, yeah, but and that's, they all say that, but it's exactly backwards. They're deriving it backwards, and it's not Newton's equation. And there's no... You know, I've sort of found the gimmick. The gimmick is acceleration. There's no such thing in Newton's physics. I mean, Newton's just talking about the change in velocity.
Newton say F equals ma?
So he never said F equals... No, he just said that force equals the change in your momentum over the time. So it could be a rate, or you could just do the total time. But he never said F equals ma. He didn't, like I said, he never used the concept of acceleration per se. He just used change in velocity. So he never said anything about any notion of a rate of acceleration. And so that's where they've broken it, is there's no... If you put the actual rate of acceleration into their F equals ma, you won't get the right answer. Because the mass times the rate of acceleration won't tell you how much force was applied. You have to assume that you're doing it per second. You know what I mean? You'd have to presume you were just wanting a per second answer instead of a total answer.
To make F equals ma.
Right.
But then how does weight work at all then, right?
Right. If you want to know
that, it gives us weight, right?
If you want the total force, you have to know how long the rate was applied.
As it was applied. Yeah. Okay. Yeah.
That's where they cheated the experiment, and they also cheated, like I said, with the simple one that rates are usually
they have to know how
per second, and anything that's per second, they write as squared. And that's a big mistake. The fact that something reoccurs every second doesn't give you a right to square it. And they write it. The notation is wrong. They write per second as seconds squared.
They do? What's wrong with that? Why is that?
Because you're not squaring the seconds. Right? I mean, counting 1, 2, 3, 4 is different than squaring. Something happening every second is different
per second.
Right, is different than squaring a number. Right, per second means it's just continuous. It doesn't tell you how long it happens. It just tells you for every unit of time, there will be a new unit of this volume. I mean, you're just dropping pennies, right? I drop 1 penny, I drop 2 pennies, I drop 3 pennies. That's not pennies squared, right? That's not pennies squared. That's pennies per increment of time. So I say you can't write the same notation for 2 completely different functions. One function, you're dropping a penny every second, and the other function, you're squaring 2 quantities. Right, a length and a height.
Then why do they square it?
Because it looks good. It looks right. Per second looks okay as squared. But I'm just saying the notation is wrong because it's not a square. It's not per second. I'm just saying the speed, when you write 9.8 meters per second squared, it's not square seconds. It's per second seconds. You see what I'm saying? It's a square.
Meters per second.
It's not seconds squared. You don't take the number and square it.
No,
like if it was 4, you don't make it 16
in a second.
Right. Yeah. So it's you're getting a wrong. You have the wrong unit. The unit shouldn't be squared. There should be some other notation for when it's continuous.
Yeah. For it's
okay, like a continuous decimal point. You know what I mean?
It isn't the same as squared. I see your point. Squared is totally different. Squared is this, right?
Squared is a quantity. This other thing's ambiguous. It could be 1 second. It could be 10 seconds. It could be 500 years. I mean, you know what I mean? You could have any volume from a per second is any volume. and squared is a specific volume. Well, I just mean that it gives them, you know what I mean. Math is all about cross multiplying and switching.
Yeah, I know.
And as soon as you start switching that square somewhere, all of a sudden it looks like it's a real square when it's not a real square.
And then it's used as a proper square.
Exactly.
It is per second.
Yes, yeah. I'm just saying that's, those little. It's it's not a big shenanigan, but that's the kind of thing that ought to clean up. Because that's cheating.
Anyway, the point is, where we got to before we went down that particular rabbit hole, right, is go and do an experiment or find an experiment, as you say, right, that's done, because there must be loads out there. There must be lots out there that prove this one way or the other, right? There must be. I know we're coming out with our rinky-dinky stupid at-home experiments, right, which, you're right, could have such a margin of error, right?
Yeah, no, it's
someone should do it. Someone should do it.
I just think all these, it's just funny that nobody's really filmed all these elemental, even back in the 50s, they filmed a lot of stuff, but they didn't do.
Why did they never
They didn't do these kinetic energy. Well, I think they didn't do them because guess what? The answers don't come out quite right. Their theory really isn't validated doing those experiments, and that's why they didn't do them. They just said, hey, this experiment didn't work. It's like Lewin and his clay, The experiment doesn't work.
Really? But are you telling me that every person who's got an air track has played around with it and done this experiment and gone, it doesn't work?
Well, I think they're saying that in the sense that obviously everyone we've seen online, they don't tell you the masses, right? Because if they told you the masses, then they'd have to admit, we couldn't get it to work with the half masses, proportional masses, a 2 and a 1. Yeah, the experiment doesn't come out right. I can make it look good, with 3 to 1. Or 4 to 1, but 2 to 1, I can't.
We still should find someone with an air track, because an air track's a good way to do it, right? I think the air track is, you're taking the gravity out of it. It's very smooth. An air track would be a good way to do it.
I think it's a good air track, just because. But there's so many ways. You have to have somebody doing it who's honest, because, like I said,
no, it's got to be honest and competent.
You make that track a little bit.
I know.
You tilt it just a tiny bit. All of a sudden, it's easy to make. It's easy to make free energy. Free energy. No,
it's got to be someone who's. And I'd really like to see the multiple. If the first experiment worked, the Lewin experiment worked, I'd love to see the one I've said there, where you bash 3. What was it? By 3, you're doubling it, right?
Right.
That is very noticeable. That isn't a mistake on your. You could see that on film, right?
Well, like I said, I could make the machine where if I bang that into a lever, I can restart the same thing all over again. And so I've doubled the energy. The lever doubles it again. Then I double it going back the other way. So by the time I go one time around, I've got 500. I've 5 times as much energy by every round. But I could definitely.
As I say, rather than complicating it, I just want to see 3 bashed into each other. You could probably, on a good track, does it matter? Doesn't matter the distance they are apart. So
right.
Why do they always, when they shove them into each other, why do they always have them quite far apart?
Well, I think it makes it easier to see the exact collision take place. You really couldn't see everything that happens if you do it in too small an area.
Together, but that distance shouldn't matter, right? So you could get 3 on there. You could get a 1, a 2, and
no
a
problem.
4.
As long as there's space between the springs is all you need.
As long as there's space, the distance doesn't matter.
Yeah.
As long as you can measure it as well going through the gate.
Yeah.
Yeah. So you need your gate,
Or very good video. Either way.
Yeah, or really high-speed video. The high-speed guys could do it. Come on, there are so many YouTubers out there. Please, if some YouTuber just happens to watch this, please just invest you guys do this all the time, $1,000 just to prove us wrong. Just, do it right, of course.
Yeah.
Make sure it's level. The problem is we're talking about something where you probably need some experience of using the air track for a bit, right? I'd need a day with it to really suss out how it works.
Yeah, I'm not opposed to other ways. Like I said, there's lots of other ways to make things that are relatively frictionless. And the point to prove is really it's so simple. Like I said, it's just this idea of bang something into a spring, frankly. I mean, that's all they need to do is just bang things into springs.
Yeah, as you say, bang something
just
into
keep
a spring.
Proving that 5-ton train going 10 miles an hour has twice the energy of the 10-ton train going 5 miles an hour. And I'm just saying they're never going to make that real. That's never going to be true. You're never going to be able to give extra momentum to anything. And extra momentum is free energy. I'm just saying, I'm pretty confident that that's...
Yeah, I think I want to go and look again. I'm going to do some more study and just go away and look again at train crashes. And there must be things that people are doing where they're bashing things into things, right? Because that's where you'd see it, right? That's where you would most see it, I think, in collisions. Yeah.
Yeah, but I
I
mean,
think anywhere else that we would see it, I can't. How about ballistics? They must look at this. Like, so many people must have looked at this, though, Gary. Right?
well, you would think they would have figured out that there's not 2,000 joules
Yeah.
in the bullet and only 2 joules in the gun. I mean, that's a outrageous difference in the energy. Right here, you had an explosion, and somehow there's 2 joules going this way and 2,000 joules going that way in the bullet. How could that be possible and Newton's third law still be real? But that's how the kinetic energy, it just exaggerates and exaggerates. So the faster and faster you get something going, it's making more and
because
more
you've got your
energy.
small lead bullet.
Right. So even though it's 1,000 to
the muzzle
1,
speed is like that.
if you do it by money, if you do it by just thinking about the fact that you have 1,000 times more atoms going 1,000 times slower on one side, and you have 1,000 less atoms going 1,000 times faster on the other side, you have the same money, right? I mean, 1,000 pennies is the same as the $10, right? Or whatever. I should have thought of that ahead of time. It's probably $100. But anyway, I'm just saying that if you think of in dollar bills or $100 bill,
$100, isn't it?
So just think of it in terms. Well, just think of dollar bills and $100 bills.
No,
It's just about currency,
Right. 10, wasn't it? 1,000. Yeah.
Yeah. Well, I'm not. I'll catch fire if I'm forced to do too much math on the spot. Things will start. Sparks will fly out. I'll be given away.
So you're right. Like the ballistics, cannonballs. There must be so many times in history when people have come across this. We should. Have you tried? So many YouTubers out there, right? Surely one of them would want to look at this.
Yeah, somehow I am really hateable. So nobody.
Yeah,
they won't even respond to my emails. I mean, I send emails offering money. I'll pay you for your time. I really want to discuss this.
No, I mean, I think you probably just cooked your own goose just by getting understandably upset about this, and then you came over in the wrong way, and I think that's why you.
Yeah, it is. I just can't charm anybody.
That's what I mean. Maybe you don't present. So I don't think they really want to touch it either, which is interesting.
Well, that's what I think. I think that's the game.
Yeah, I think they're looking for any excuse.
You start to look at it. You say this. Yeah, that is a little bit weird. You say, well, yeah, how could it be free energy? That doesn't work. I don't really want to try to defend that, because I might look stupid. So they run away.
I think that's the thing. And just. Probably I don't really care.
Nothing.
And also I'm not qualified, right? Because all the people I contacted, I could see the reticence. They don't want to touch this, right? Because I think a lot of them have got burnt with the whole flat Earth thing.
Right. Well, and this isn't flat Earth, right? I mean, this is
almost worse.
I'm just saying this is dangerous. This is dangerous. Yeah. Right? I mean, flat Earth is easy because they're wrong.
Yeah, exactly. They're wrong. I agree. Imagine this: that you started pulling that string. And the whole freaking jumper unravels on you, right? Yeah. These people have spent a life in science. They really genuinely don't want to go there. I see why, right? It's fair enough, right? We've got most things answered, right? This is just a small relative thing. It doesn't really matter because we don't really use kinetic energy. It'd be great to find somebody who does use kinetic energy because they would know this, right? They would know this. Does anybody?
There's no profit in it because it won't work. You'll never get it to pay off. So I guess the point is wherever it's serious, like if you're doing heart surgery, you're using momentum. You're doing space travel, you're using momentum.
Momentum.
Anywhere it counts, or your life is on the line, you're going to use momentum because it gets right answers.
I mean, this is the odd thing, right? That anywhere that you get engineering, right, and I've had a fair amount to do with some engineering, right, the theory is there. Often it sort of comes later, and it does hint at things that you would want to look at, right? I'm not saying it doesn't, but generally when they actually get into it, things don't quite work, right, and there's all these other conflating factors, right, and engineering is often complex, right, and the answers are normally quite complex as well, aren't they, right? I don't know if you've seen those interesting videos where they managed to suspend in like compressed air, a certain shape of a screwdriver that floats, and like weird Venturi things that shouldn't really quite happen, and laminar flow, and all these kind of effects, the Magnus effect. There's all these really quite interesting things that are. The explanations are quite complex.
Right, and they've broken, I could think, the connection to how simple it could be. It's like I think of that with resonance and sound. because all of that is really about adding energy to a system, and you have to add it when the thing's moving in the right direction. So if you want to add energy to a pendulum, you have to add it when the thing's moving in the right direction. If it's moving against you, you're not adding.
You can't add it.
So that's not resonant. That's not a resonant frequency. So only the frequencies that add at the same rate, at the same time it's moving in the right direction, can be resonant frequencies. You will add energy to the system.
Yes.
And so it's a really simple idea that, it's just about adding energy, And that's why the tone gets louder and louder, is everything that's going in the right direction keeps getting being kept, right? You're keeping everything going the right
direction. Plus a bit more.
And you get rid of everything that's going the wrong direction. And so, so it becomes, it just amplifies this one tone or this one frequency that's the common denominator, right? You're looking, it just says what's the most common thing we have in common, these three things. And it just says that's my resonant frequency. I'll really be powerful if you stay on that one, And it's just so it's a simple. I'm just saying it's another indication of something that, to me, I wish somebody would have said to me 50 years ago. That simple explanation, because I was confused as hell when somebody said resonance. I was like, well, how do they know what they like, and how does it know what tone? And I had no clue about how simple it could be understood.
Yeah, resonance is a very interesting one, isn't it? Did you see that experiment on, was it Mythbusters, where they made the Tesla resonant, his earthquake machine?
No.
Tesla's, No?
No, I didn't see that, no.
Okay, go and watch that one.
I don't watch TV ever, but anyway.
No, it's on YouTube.
Yeah, I should be able to find Mythbusters.
Mythbusters, it is definitely, because I saw it on YouTube. I don't watch TV.
Okay, so it's a Tesla one. So I just look for Tesla and Mythbusters.
Like Tesla earthquake machine.
Okay.
Have you not heard? So, have you heard the story?
No.
Ever? All right. So, because we were talking about Tesla earlier, very quickly, before I go, right, I've got to go have some lunch, something to eat, whatever, a cup of tea. I'm British. So, there's this myth, and I think it is, well, we don't know. So the myth is this, right? And the audience will love this. No one's watching this far anyway, so only one person will probably see this, and that'll be you reviewing the video. But the idea is that when Tesla was living, I think, in San Francisco, and I'm associated with earthquakes, but it could have been in New York when he had one of his labs. He got a new building, and the building was all like iron struts and things, And at the time, he was working on a lot of resident devices. I think he was trying to make a sort of new. He was working on the AC motor, right, that resonated backwards and forwards and vibrations and stuff. He had the egg. I think, have you seen the egg that he put?
Well, that was the first version of the motor, right? The
exactly,
phase,
where the egg actually went round, and then he tried to contain it anyway. So he was working on that, and he came up with a very neat, and he patented it, actually. There is a patent of his, because you know what he's like. He loved his patents, right, to get his backers to back him. And so he came up with this. So it doesn't disturb us. He came up with this machine that vibrates, basically, right? But it vibrates very, very, very consistently. And he hooked this machine up to one of the girders, and he turns it on.
Right, this is exactly, okay, so yes, the concept, I've actually thought of that concept, that's exactly how you get energy to a building, is you could just keep doing it at the right resonant frequency, the reflective frequency of the building, and you can just, a woodpecker could knock the building down theoretically, just because of the fact that as long as you keep adding and you're never subtracting.
Well, that's exactly what he does. He leaves it on and he goes for lunch. He comes back. This is how the story goes, right? So some of it we know is true, some of it may be fame. And he actually starts to see the building is shaking and the earth is starting to shake, right? Because obviously the building is connected. Right. It's got these big girders, right? He runs in, and the police are also sort of coming in because they're going, this building's shaking, what the hell is going on? And there's a bit of a racket, and literally it's all moving. So, other people outside are hearing about it. And he gets a sledgehammer, and they come in, and Tesla's just bashed this machine with a sledgehammer, literally, as a way to stop this thing, right? Why he didn't turn it off, I don't know. Maybe they made it more dramatic in the whatever.
Well,
but anyway.
That you would think, that, there's
but I mean, the theory is sound, it would work.
Exactly.
He welded it, I think, actually, to this girder, and it's just a tapping mechanism, but because it's tapping at this resonant rate, the whole thing starts.
Well, you have they have that famous bridge, that just blows over. It's a suspension bridge, and it just starts wobbling and wobbling, and then it eventually falls into pieces.
So this is why you want to watch it, because then Mythbusters, they try all this stuff with drills, trying to get the same stuff. And the point is, they give up because I won't spoil it, but they give up because basically you cannot replicate something that, because it really has to be exactly the right frequency. Whereas a drill has got a bit of slip and it's a bit sloppy and it's not quite right. Anyway, so they give up, and then they find the other guy in their unit has actually got a solenoid, right, which you can put to a rate, and is actually a very, very accurate thing. And they then go, and I watch it, they then go and test it on a bridge, right? Okay, a small bridge, right? And I'll leave it there, watch it, because you'll enjoy it, right? It's such an interesting thing, right? And you suddenly realize in this video, in their videos, it's Mythbusters, Tesla earthquake machine, I think they call it, right?
Yeah,
and you'll enjoy it, Gary. I promise you. You'll
thanks.
go, yeah, I really enjoyed that.
Yeah, but like I said, that's an idea I'd thought of just from that bridge video. Actually, is what started me thinking
Where
about
they do
the whole
this.
idea
You don't actually need as much energy as you think.
It's
right?
a tiny wind, right? It's like a 20-mile-an-hour wind.
Yeah,
you know, and
yeah.
it wasn't in one direction. But the key is because of the cavern it was going over, it had a common frequency, so it just kept adding the energy from both sides. You know, and it just swung it.
You know, and it's a very powerful thing, right? All the people marching over and demolishing bridges in the army, right? When they march over and the bridge collapses and all that kind of stuff, right? Because they're in step, they have to break step and everything. But watch the video on the earthquake machine, because So what do I think about it? I think he probably did make something. I think it probably did have an effect. Whether the police were rushing in and sledgehammers and all that, I don't know. But you know, like some of the Tesla stories, I don't believe. Right? There's a Tesla story about he had an electric car and he drove around, and I probably don't think that one's very plausible, right? But the earthquake machine is simple enough. He was, at that time studying that.
He did have an electric boat. So he actually, he made a radio-controlled boat.
Oh, he did, definitely. Yeah, radio-controlled wireless boat.
Which is kind of amazing for, the technology of the time. That was
incredible. Yeah. And, again, I think he was very good at exploiting other people's advancements, right? He was a really good tinkerer. And he was very good, like me, he was very good at taking a couple of ideas and putting them together as well, I think. Right?
Yeah, I think it was like a counterfeiter. But he didn't even have the, it's like one of those promotion people. You know what I mean? They take the raw talent and they can make it into something. So he was good at taking little pieces from the world and putting it together into
putting them into something that really captured the imagination and got some money behind it. Because also he had a really good guy working for him who was his fabricator, who worked with him for 30, 40 years, do you remember the guy?
Yeah, because Tesla didn't look like a guy who got his actual fingers too dirty.
Fingers with his shirt like this and everything, and his hat.
Oh, he was a little, you always found that one a little suspicious. And he did mock almost Edison, the whole idea of sweating. He kind of thought of Edison as he's the 90%, 99% perspiration versus 1% inspiration. And Tesla saw himself as exactly. He could have saved himself 1,000,000 man-hours of work by doing 10 minutes of thinking. Yeah. That kind of attitude. So
he was a dick, right?
Yeah.
He was a dick. Not that Edison probably wasn't either, right? But. Edison was a grafter with all his perspiration, right?
Well, I just mean his hands were always in it. He didn't, there was probably very little that had his name on it that didn't have his fingerprints on it.
That didn't have his fingerprints in it, exactly. That's right. Whereas I think Tesla are the opposite. They were going around electrifying these elephants to show how dangerous this AC current was. Right? They just up the amps, burn the elephant. Oh, it's really dangerous.
Well, they were going to shoot him. They were going to shoot him anyway, but
it's really safe DC. Just see how safe DC is across your heart, right? It's funny times there. Right, I got to go. It's always a joy and a pleasure to speak to you, Gary.
All right, it was good. Yeah. And so we'll do it again.
We'll definitely do it again.
Okay.
Yeah, and hopefully someone out there.
Well, hopefully we'll gain some piece of something we can grok and we can hold on to.
Go, someone's done this. That's really helpful.
Yeah.
And watch the earthquake machine thing because you'll enjoy it. It's definitely on YouTube. I promise you. Because I don't watch, like you said, right? I don't watch it. So they'll have it there. All right. Speak soon. Bye.
It's good. Thanks. Bye. All right. So that worked mostly, right? Yeah. There's my camera behind my camera. So anyway, he got a better view of the board than you did, but tough. I don't know what I can get rid of here. that went away. Okay. All right. So we'll just get the hell out of here before something goes wrong. So anyway, till the next time and such, and so forth and whatnot. Yeah, it's been at draftphysics.com. I don't know where the logo is. It shouldn't be here, but whatever. Till the next time and such.